Hello, with a group of two from the B division, myself Pratmesh Fadia and Dhruv Goel. The title of our research paper is an evolutionary multi-objective genetic algorithm to solve 0-1 knapsack problem. This research paper was published by the IEEE in the year 2009 by the author named as Mrs. Sachi Nandan Monti and Mr. Rabinaran Satapathy. Now let us have a detailed introduction about the research paper. As we know, the 0-1 knapsack problem is widely used due to its practical importance. In the last few years, the generalization of this problem has been studied and many algorithms have been proposed. Now, evolutionary approach for solving the multi-objective 0-1 knapsack problem, which is one of them, many real-world papers founded in the literature about multi-objective knapsack problem and also about the algorithms which were introduced for solving them. In this research paper, we introduce a new evolutionary approach for multi-objective 0-1 knapsack problem. We have used the genetic algorithm in order to determine the solution quality. So what is 0-1 knapsack problem? The 0-1 knapsack problem means that the items are either completely or no items are filled in a knapsack. Let us understand this through an example. If we have two items having weight 2 kg and 3 kg respectively, if we pick the 2 kg item, then we cannot pick the 1 kg item from the 2 kg item, which means we have to pick the item as a whole. The item is not divisible. This is a 0-1 knapsack problem in which either we pick the item completely. The 0-1 knapsack problem is solved by the dynamic programming. The dynamic programming is the solution to the 0-1 knapsack problem. Problem description. Knapsack problem is a problem and combinatorial optimization. Given a set of items, each with a cost and a value, determine the number of each item to include in a collection so that the total cost is less than a given limit and the total value is as large as possible. We have n kind of items. 1 through n, each I has a value pi and weight wi. The maximum weight that we can carry the knapsack is c. The 0-1 knapsack is a special case of the original knapsack problem in which each item of input cannot be subdivided to fill a container in which that input partially fits. The 0-1 knapsack problem restricts the number of each kind of item xj to 0 or 1. Maximize, subject to summation of I equals to 1 to n, where wixi is less than or equal to c, where c is the maximum weight that we can carry the knapsack. So now the multi-objective algorithm which was proposed by the research paper in order to solve the 0-1 abstract problem is as follows. Step 1. Start. Encoding. It represents the individual. Generate random population of n chromosomes. Suitable solutions for the problem. Step 2. Fitness. It evaluates the fitness of each chromosome. Step 3. New population. It repeats following steps until the new population is complete. Step 4. Selection. It selects the best two parents. Step 5. Crossover. It crosses over the parents to form a new offspring or children. Step 6. Mutation. With the mutation probability. Step 7. Accepting. Place new offspring in a new population. Step 8. Replace. Use new generated population for further run of algorithm. Step 9. Test. If the end condition is satisfied, then it stops. Step 10. Loop. Go to step 2.
Now, we come to the pseudocode for the 0-1 knapsack problem. The pseudocode for the problem is given below. Now, for the complexity analysis, the time complexity of the 0-1 knapsack problem is big of 2 raised to power n, as there are redundant subproblems, and auxiliary space complexity for the 0-1 knapsack problem is big O of 1, as no extra data structure has been used for storing values. Now we come to illustration. First, encoding. In the encoding scheme, randomly the items are selected. If the item is selected, then that is represented as 1, and if the item is not selected, then that is represented as 0. From the above figure, the items selected are 1, 3, 5, and 6. Suppose randomly populations are generated and are represented as chromosomes. Generated random population of n chromosomes are 0, 1, 0, 1, 0, 1, 0. Second, double 1, double 0, 1, double 0. And third, 0, 1, triple 0, double 1. Now we come to fitness and selection. The second step, fitness and selection. For the first chromosome, the total benefit and weights are to be calculated. The total benefit is 19 and total weight is 24. Then we must check whether these items can be selected or not. As the weight exceeds as the weight exceeds our maximum capacity, so we cannot select these items for further steps. For the second chromosome, that is for 1100 the total benefit is 20 and total weight is 19. Here, these set of items can be selected as weight is less than our maximum capacity, that is 22. Similarly, for the third chromosome, 01 the total benefit is 21 and total weight is 18. From the above discussion, it is clear that second and third chromosomes are selected as parents, upon which the crossover will be operated in order to get the child chromosomes. Now, for the third step, we come to crossover and mutation. The selected chromosomes are 1100 which is parent 1, and 0100 is parent 2. After crossover, the resultant offsprings will be 1100 child A, and 0100 child B. If we put the mutation over the child 2 and on the last bit, then 0 will be converted to bit 1. Before mutation, the value is 0100 but after mutation it changes to 0100 After the crossover is finished, the new offspring are kept in the new population. If the end condition is there, then the process will stop there. Otherwise, again the fitness calculation and selection will occur to find out the better solution. Now we come to conclusion. In this paper, we have proposed the most effective evolutionary algorithm, which is derivative-free stochastic optimization methods based loosely on the concept of natural selection and evolutionary process for solving 0-1 multi-objective Knapsack problem. This algorithm uses the genetic algorithm concept. For these experiments, one knapsack and 5 items are considered, and a comparison to other existing method is also considered. Here is the bibliography, and thank you.